All right, so hope you all enjoyed quiz 2, and I think it's not that difficult to you, right? Because it is open book already, and the calculations is not that hard. So if you find the right equation, you find the right criteria, then you can answer each of the questions, right? All right, so let's get back to the lecture. Then in the control, as I mentioned, there are 3 lectures. The first lecture is the lecture before last week, and we introduced the linear continuous time system. Then in the lecture in last week, we introduced still the linear system, but it's discrete time system, which means the time is not continuous. And we have lots of examples that we can formulate the control system from the actual or the real questions for both continuous and discrete time systems. Then today we are going to talk about a more realistic case, which means it is still discrete time system. It is still discrete time system. Then it is nonlinear. It is nonlinear. Then in the previous lectures about a linear continuous time system or discrete time system, if you remember, we first introduced the formulation. And then we introduced the idea about the stability. So if the system is stable or not. Then if it is not stable, we introduce the pole placement and the optimal control. But before that, to check if the system can be using the feedback control to do the pole placement or optimal control, is we also need to check the controllability as well, right? And if you remember in the discrete time system or the continuous time systems, the criteria about stability they are a bit different, right? They are a bit different, and for the controllability they are exactly the same. I mean, the way to check that is exactly the same, and the difference is also in the solution as well. So the solutions for the linear discrete time system or the linear continuous time systems, they are different. They are different. And in the hand activities, you play with some examples and also solve the problems in Matlab and some coding functions, right? And today, as I mentioned, we are introducing the very last part of the control, which is the nonlinear discrete time system. So it is still discrete time system, but it is nonlinear instead of linear. So which is quite close to the real case, because in most of the cases in the real, then it is nonlinear system instead of linear. So linear is the easiest case. But for the nonlinear discrete time system, we mainly analyze and introduce it based on what we have in the linear case. Then I will show you a little bit later. All right, so the general formulation of the difference equation for the nonlinear discrete time system is as what we showed here. So as we can see, it is still xk and xk plus 1, then which means that is a discrete time system instead of continuous time system, right? So if there's a t and there is an x dot on the difference equation, then which means that is continuous time system. If there's no dot on the x, then which means you can't calculate the derivative of x with respect to time, then which means that is discrete time system. Then the relationship is between xk plus 1 and xk, right? So that is the discrete time system. But why is not linear? If you remember, in the linear discrete time system, the difference equation is xk plus 1 is a linear function of xk and xk and uk. Then which means xk plus 1 is equal to ax plus bu, if you remember. That's for the linear case. But for the nonlinear case, here, the xk plus 1, so which means the state in the next step is a nonlinear function of xk and uk, then which means xk plus 1 is equal to f, x, and u. Then f is a nonlinear function, or a set of nonlinear functions if x and u have multiple dimensions, right? So this is a general formulation of a nonlinear discrete time system. It's about that, all right? And in the nonlinear discrete time systems, as I mentioned before, so the both x and u can be multivariable state, right? It can contain multiple variables in it, then which means your f, the nonlinear function, which presents the relationship between xk plus 1 and xk and uk, it can be multiple functions as well. Right, that's for a general case. It's a multifunction as well. So if you remember, in the linear discrete time system, it's ax plus bu. Then a and b can be matrices. Then the x and u can be multiple variables in them. Right. So that is the nonlinear discrete time system for multiple variables. Then you have multiple f functions in the nonlinear case. Then different from the linear case. In the linear case, you can directly use a matrix to present A. Then it can handle the multiple variable case. But in the nonlinear case, because it's not linear anymore, then we need to use multiple functions if we have multiple variables. And I will show you some examples a bit later. Right, and the output of the nonlinear discrete time system, it also can be nonlinear. Then which means yk is equal to h, xk, and uk. Then which means the function h is nonlinear. Then the output y is a nonlinear function h of the x and u. And again, because the x or the x or the y, they can be multiple variables, then the nonlinear function h can also be multifunctions as well. All right. Then comparing to the linear discrete time system I mentioned before, the nonlinear the linear discrete time system, it can also be multifunctions, but because this is linear, we can summarize the multifunctions to the matrices A and B. Then we can rewrite the multifunctions, difference equations into a general formulate as xk plus 1 is equal to ax plus bu. Then AB can be matrices with corresponding dimensions, right? So in the nonlinear case, the difference is we use f and h instead of a, b, c, and d for the difference function and also for the output functions. Then which means the difference function f is a linear function or a set of nonlinear functions, right? And the function h is also nonlinear function for the output. And again, the x, y, and u, they can be multiple variables. They can be multiple variables as well. All right, so that is the nonlinear discrete time system. And again, the same thing for the linear discrete time system is still a relationship between xk plus 1 and xk. So there's no dot on the x because it's not continuous. You can't calculate the derivative. And also the difference equation is a relationship between xk plus 1, between xk plus 1 and xk and uk. And the only thing is the functions are nonlinear, which means it's f and h instead of a, b, c, and d matrices. All right, so that is the general formulation or standard formulation of the nonlinear discrete time system. Then a very good, a very important point is the equilibrium in the nonlinear discrete time system, because the nonlinear system is too hard, is too complicated to analyze on it. Then we will introduce equilibrium, and then we will do all the analysis on the equilibrium points. Then what is equilibrium point for the nonlinear system? So a constant trajectory generated by a constant input function is called equilibrium. In short, what is equilibrium point? An equilibrium point is if you have a constant input. So if you have a constant u, then you will find a constant state that state will never change forever. You know what I mean? So the equilibrium point means if there's a point with a constant u, with a constant input u bar, then if you have an x bar, which is the state that the state will never change, the system will not change forever, then that is equilibrium point. All right, so in short, the equilibrium point means for a nonlinear discrete time system, and the equilibrium point means the system or the state will never change on the equilibrium point. All right, I'll show you some example. So the question is, we know the equilibrium point, but how to calculate the equilibrium point? How to calculate the equilibrium point? Because we know at the equilibrium point, the state will never change, will keep the same forever, right? Then which means xk plus 1 is equal to xk. Is that right? So at the equilibrium point, the xk plus 1 is equal to xk, because at the equilibrium point, the state will never change. Then which means the state at the current time step k is equal to the state for the next time step xk plus 1, right? We will use that to calculate the equilibrium point. Let's look at the example together. Let's look at this example together. So suppose we have an suppose we have a nonlinear discrete time system. Is xk plus 1 is equal to a quarter of xk squared plus xk and minus uk, minus 2 times uk. And when u is constantly equal to 0.5, what are the equilibrium points? So the first thing about this is the equilibrium point, the control is given. The u is constantly equal to 0.5. Then we put 0.5 back to this equation. Then this term comes to be 1, right? And the next step is because we know xk plus 1 minus xk is equal to 0, right? Then we use that equation. We formulate xk plus 1 minus xk. So xk plus 1 is equal to this equation, right? This is from the system. And this system minus xk, so this equation is xk plus 1, right? Then we know xk plus 1 minus xk is equal to 0. Then which means this equation minus xk is equal to 0. Then we have this equation, which is a quarter of xk squared minus 1 is equal to 0. Then which means we suppose xk plus 1 minus xk is equal to 0. Then we solve that equation. And the solution of x are the equilibrium points. And in this case, the x bar is equal to 2 or minus 2. So there are two equilibrium points. There are two equilibrium points in this case. One equilibrium point is x bar equal to 2 and u is equal to 0.5. And the other equilibrium point of this system is x bar equal to minus 2 and u bar is equal to 0.5. So which means there are two equilibrium points in this nonlinear discrete time system. And you know how to calculate the equilibrium point already. All right, then that's the another example. So here's an activity, but we don't have time to do it on the class. So please practice the activities in this lecture by yourself after the class. All right, so this activity is a little bit complicated because we have multiple nonlinear functions for the nonlinear discrete time system, and also we have two variables in the state, which is x1 and x2. But it will be similar, so don't worry about it. It will be similar. Let's look at this activity together. So again, we want to calculate when u1 is constantly equal to 0.5 and u2 is constantly equal to 1, what are the equilibrium points? We want to do that. And again, the first thing is you back substitute the 0.5 for u1 and 1 for u2 back to those two equations. All right, that's the first step. And then the second step is you also need to formulate the xk plus 1 minus x1 equal to 0. All right, so in this case, we have two functions. We have two variables, then we can get two equations. The first one is x1 k plus 1 minus x1 is equal to 0. Then the first equation is the same as what we have in the previous example, right? So xk plus 1 is equal to this. This one minus x1 is equal to 0, then we have this. We have this equation, right? Then the second equation we have is about x2. Then x2k plus 1 minus x2 is equal to 0 as well. And we know what is x2k plus 1. Right, so x2k plus 1 is about this equation, and minus x2 is equal to 0. Then we have the second equation here. We have the second equation here, and then let's look at it together. So because from the definition of equilibrium points, the state will never change at equilibrium point, then we have x1k plus 1 minus x1 equal to 0. x2k plus 1 minus x2 is equal to 0. Then we have the two equations already. And we have two equations, and we have two variables, which is x1 and x2. We can solve it. And after we solve it, and those points are the equilibrium points. All right, and let's solve the question together. If we only look at the first one, if we only look at the first equation, and we solve that already, right? We can directly solve x1 from the first equation, and we get the answer already in the previous example. Then, which means the solutions for x1 are 2 or minus 2 from the first equation, right? Then we can consider them separately. So when x1 bar is equal to 2, and we can back substitute 2 to the second equation. And then we have the second equation like this, right? We put 2 back to the second equation here, right? Then we have this equation, right? From the second one. Then from this equation, we can have x2 equal to 0 or x2 equal to 4. right? So in this case, when x equal to +2, we have two equilibrium points. One equilibrium point is x1 equal to 2, x2 equal to 0. And the second equilibrium point is x1 equal to 2 and x2 equal to 4. Right, so for when x1 is equal to 2, then we have two equilibrium points. Then let's consider when x1 is equal to -2. And also we replace x1 here by -2, then we have the second equation like this. Then for that equation, we also have two solutions for x2, right? Two solutions for x2. Then which means when x1 is equal to -2, then we have another two equilibrium points, right? So which means for this, nonlinear discrete time system, we have four equilibrium points. Right? So that is the way to calculate the equilibrium points. It is quite simple. If you just remember to formulate xk plus 1 minus xk. So how many variables in the state, then how many equations then you can formulate, right, for the xk plus 1 minus xk. And you know xk plus 1 in the standard formulation already. Then you use xk plus 1 minus xk equal to 0, then you have the function. You have the equation. Then solve the equation together, and the solutions are the equilibrium points. And you can have multiple equilibrium points for each of the systems, the nonlinear systems. All right, so that's the equilibrium points and how to solve the equilibrium points. Then if you remember for the discrete time system, we can do the discretization, which means we can transform a continuous time system, linear continuous time system, into discrete time system. But in the nonlinear case, we can also do some transformation, but not from continuous to discrete. Not from continuous to discrete, but from nonlinear to linear, which we called it linearization. Then which means in the linearization, we can linearize the nonlinear system to get a approximated linear discrete time system. But the thing is, this inner linearization can only be done on the equilibrium point. All right, so the linearization can only be done at the equilibrium point, at one of the equilibrium point. It can be linearized. It cannot be linearized at any point of the state. It can only be linearized at the equilibrium point. Again, it can only be linearized at the equilibrium point. The linearization is quite simple. It just uses the first order Taylor expansion. First order Taylor expansion to do the linearization. And suppose, wait a minute. Suppose we have the nonlinear discrete time system. Xk plus 1 is equal to fxu and y is equal to gxu. Then an equilibrium point, which means u bar, x bar, and y bar. That's the equilibrium point. If we want to do the linearization at that equilibrium point, the linearization is something like this. is delta x k plus 1 is equal to a delta x plus b delta u. And delta y is equal to c delta x plus d delta u. And the a, b, c, and d are the partial derivatives, or we call it Jacobian, the partial derivatives of the function with respect to the to different state, right? So for a is the partial derivative of the nonlinear function f with respect to the state x, and also evaluated at the equilibrium point. And matrix B is the partial derivative of f with respect to u, and also evaluated at the equilibrium point x bar and u bar. And the matrix C is the partial derivative of the function g here, with respect to the state x, and also evaluated as the equilibrium point. And the matrix D is the partial derivative of g with respect to the control u, and also evaluated at the equilibrium point. I will give an example a little bit later. So which means if you have a nonlinear discrete time system, then you have an equilibrium point. Then if you want to do the linearization at that equilibrium point, then the linearization is something like this. And you can calculate the A, B, C, and D by calculating the partial derivatives of the f and g. And also the partial derivatives, wait a minute. The partial derivatives, wait a minute, it's telling me I must restart. Yep, should be right. All right, so the partial derivatives are evaluated at the equilibrium point. That's why we need an equilibrium point at that point to do the linearization. And also, if you come back to the system, it is delta x instead of the original x anymore, right? It's delta x dot y and dot u instead of the original x, y, and u. And for delta x, it is x minus the equilibrium point. For the delta u is the u minus the equilibrium point u. And for the delta y is y minus the equilibrium point y. So that is the linearization. And let's give an example about the linearization. So suppose we have this nonlinear discrete time system. We have it before. So we have it before. That is what we have to calculate the equilibrium points, right? And first we can calculate the partial derivative of the function f with respect to x. And in this case, we have two function f, which is f1 and f2. Then we also have two variables, which is x1 and x2, right? So we can calculate first the partial derivative of x1 with respect to x1, and that is equal to that, right? So if you calculate the partial derivative of this equation with respect to x1, and if we calculate the partial derivative of x1 with respect to x2, then in this equation there's no x2, then which means that is 0, right? Then if we calculate the partial derivative of f2 with respect to f1 is this equation with respect to x1, then that is equal to 1, because there's only x1 here. Then if we calculate the partial derivative of f2 with respect to x2, then we have this. We have 0.5 times x2, right? So we calculate those kind of partial derivatives, but they are functions. They are functions. Then if we want to linearize the nonlinear system at the equilibrium point x1 equal to 2, x2 equal to 4. If we want to linearize it at this equilibrium point, then we need to back substitute those two numbers onto those partial derivatives, which means those partial derivatives will be evaluated at this equilibrium point. Then if we replace x1 equal to 2, x2 equal to 4, then we have A matrix like this. And B matrix, because it is exactly the same. So if we calculate the partial derivative of u1, then that is 1. That is 2. If we calculate the partial derivative of u2, then that is 2 as well. Then we have B matrix like this. And A matrix, this value is from this. And this value is from the F1 with respect to X2. And this value is from the F2 with respect to the X1. Then this value is the F2 with respect to X2. But again, it needs to be evaluated at the equilibrium point. That's why you have numbers here. All right. And then if we want to linearize it at another equilibrium point, which is x1 equal to 2 and x2 equal to 0, then you just replace x1 equal to 2, x2 equal to 0 to those equations. Then you have your A matrix like that, and B matrix will be the same, right? So if you linearize it at different equilibrium points, then your A-B matrix will be different. All right. And here's another activity. Then that's your homework. So you need to practice about how to do the how to calculate the equilibrium points and at the equilibrium point how to do the linearization. All right. So I have the answer here. I have all the answer here. So just practice by yourself. Just practice yourself. All right. And then another idea is about the stability. So we have stability in the linear continuous time system and the linear discrete time system, right? So what's the stability for the nonlinear case? And again, this stability is also analyzed at the equilibrium point. So it is so difficult that we can't analyze the stability for the nonlinear case. But we can analyze the stability at the equilibrium point. And how to do that is at the equilibrium point, you can do the linearization, right? At the equilibrium point, you can do the linearization at that equilibrium point. And then after the linearization, you can get a linear system. You can get a linear system. Then which means for the linear discrete time system, you can analyze the stability for that. Then which means you analyze the linearized linear system, then which means you analyze the stability at the equilibrium point. All right. And for the linear system, and again, if you remember, it's exactly the same as what we have for the linear discrete time system. And it only depends on the A matrix. And the A matrix now is the partial derivative of the nonlinear function f with respect to x and evaluated at the equilibrium point. Then you have the linearized A matrix. Then you analyze on the A matrix. If all the eigenvalues are within -1 and 1, then that is stable, right? That is the criteria are exactly the same as what we have in the linear discrete time system. So that's the stability. And also that's come back to the definition of the stability in the nonlinear case. In the nonlinear case. Then which means, so if you remember, in the linear case, the stability means the state will converge to 0. That is stable, right? And in the nonlinear case, nonlinear case is a bit different, right? In the nonlinear case, again, if you analyze the linear, system, the linearized system, which means this system will converge to 0, right? The state will converge to 0. That is stable, right? But in this system, the state is delta x instead of x. Then delta x converge to 0 means your state will converge to the equilibrium point. All right. So which means in the stability of the nonlinear system at an equilibrium point, the stable means the nonlinear system will converge to the equilibrium point. That is the stability. All right, and here we gave an example. It is similar as what we have before. So this example, we deal with it for a couple of times, right? And we know there are 2 equilibrium points. And then we do the linearization. We'll do the linearization already, right? So, but it is your activity 2, but please practice on yourself. It is a bit easy because you only have 1 equation. Then when at equilibrium point x equal to square root of 2, then we can see the A matrix is 1 plus square root of 2. It is larger than 1, right? Then which means that is not stable. And when at equilibrium point minus square root of 2, then the equation is the A matrix is equal to 1 minus square root of 2. Then which means that is stable. All right. So the stability is applied, and we can only analyze the stability at equilibrium point. And for different equilibrium points for the nonlinear system, the stability will be different. All right, it will be different. And I will show you some Matlab example about the stability. Then the Matlab is restarted. Yeah, I don't know what happened. All right, so wait a minute. So I have examples about this case, So what is stable and what is not. Because you may not have a very clear idea about what is stable and what is not at equilibrium point, because at equilibrium point, the state will never change. Or will never change. But so what is the stable and what is not? Right, and I'm going to show you some examples, and that you to have a better idea about what is the stability. So this is wait a minute, what happened? Okay, so this is the nonlinear function. This is the nonlinear system we have there, right? This is nonlinear function we have here. And if we choose the equilibrium point as square root of 2, as what we have that is unstable, then that's plot what we have, right? That's plot what we have for the state. What happened? Come on. No, it's something wrong about my Matlab. All right, so I will upload those. I will upload those codes if we can't run that. So what I want to introduce here is, even at equilibrium point, you can still say it is stable or not. And why is that is, I give an example about the inverse pendulum. Inverse pendulum. So in that case, it is stable, right? So in this case, it is stable because if you don't give any input, it will never change the state, right? But any changes of the state will make it change a lot, will make it fall. So which means that is the equilibrium point, but it is not stable, right? So that is what it means. So if I can run the Matlab, then no. It's great. So I have the code, so try to practice on yourself, or I can show you in the next lecture, which means in this case, for the unstable case, when I run it, when I choose the equilibrium point, when I run it, the state will constantly the same at the beginning, and then it will directly change a lot after. And in the stable case, in the stable equilibrium point, it will keep constant at the equilibrium point. And also, I did some changes to say, if my starting point, if my initial state is a little bit offset, it's a little bit offset comparing to the equilibrium. So if the initial state is not the equilibrium, for the unstable case, it will directly diverge. And at the equilibrium point, even we give an offset on the equilibrium point, it will converge to the equilibrium, which means that is stable. All right, so let's see if I can show you a little bit later or not. All right, so that's the example. So make sure you know how to check the stability, and you have the understanding about what is stability. And for the state feedback control, it is similar. It is similar. So it is still at equilibrium point, and also it is still on the linearized system. All right. So suppose it's still that example we have. Suppose we have this nonlinear discrete time system, and when we have x bar equal to square root of 2, which is not stable, then we have this linearized system, right? We have this linearized system. Then we want to choose the state feedback control. That is exactly the same, right? So delta U is equal to minus k delta x. And we put it back into here, then we have a minus bk delta x. We have delta xk plus 1 is equal to a minus bk delta x. And it's equal to this. Then if we choose k is equal to minus square root of 2, then we can have a minus bk is 1 minus square root of 2. Then which means if we choose k like that, then the new system, the new a, which is a minus bk, is between minus 1 and 1. And that is stable, right? And that is stable, right? And we know the delta u is equal to minus k delta x, right? And is the square root of 2 delta x. But this is not the end of the solution. This is not the end of the solution. If you remember, the delta u is equal to u minus u bar, and delta x is equal to x minus x bar. Then which means if you want to calculate what is the exact u in the original nonlinear discrete time system, we need to replace delta u and delta x to there. Back to there. So here we have delta u is equal to square root of 2 times delta x. Then we replace delta u by u minus u bar. We replace delta x equal to x minus x bar. Then finally, we have uk is equal to square root of 2 times xk minus 1.5. Minus 1.5. So that is your final u. Then you can put it into the original nonlinear discrete time system. All right. So after the linearized, after you get the k in the linearized system, you also need to calculate into the original nonlinear case. Then you have your original u, which is a function of x. All right, and I also have a Matlab example, but I don't think it is running. All right, let's see if it can run. No, it cannot run at the moment. Okay, so I will show you the examples a bit later. I will also upload those codes to the UTS Online as well. All right, then there's another example. So this at the beginning it will be the same, right? So we have the same nonlinear discrete time system. Then we have want to do the state feedback control to do the pole placement at the equilibrium point at x bar equal to square root of 2. Then we do the state feedback control on the linearized system. Then we have this. We have dot xk plus 1 is a minus bk dot x, right? And if we want to make a minus bk equal to 0, and what is the u? Again, what is the u? It's not delta u, and that is your activity. So I have the answers later, but please do the activity by yourself after the class, right? So it will be similar. First, you need to calculate the delta u is equal. You need to calculate what is x. You need to calculate what is the k, and then from k you need to calculate. You can calculate what is delta u, and from delta u, then you can calculate what is u. What is u? That is here. And I also have the Matlab example as well. I will upload it to the UTS Online, and also I'm going to show you. I'm going to show you in the next lecture. All right. So that is all for today's lecture. And I know the nonlinear case is a bit complicated, and that's why I have a lot of activities and examples in the class. So please try to make sure you know how to solve every single example and activities in this lecture, and try to practice later. Try to practice later. I don't think it works. I will. I think I'll show you the Matlab examples in the next lecture. All right, so this is all for today's lecture, and we've finished the three control parts, three lectures about control parts. And in the next lecture, we will introduce the integration of sensors and the control, which is a very traditional and very classic case. That is the visual serving. So we will introduce the visual serving in the next lecture. And that's all for today. And thanks a lot. And let's move to Malin for the hand activities. Thank you very much.
Thank you, Liang. Let me get my screen. All right, so go and download week 9 material, I believe. Let me just double check.